Hi, and welcome back to the last video of the second week of the Extreme Value Theory course. This video is going to summarise all of the material introduced in Chapter 3 of the notes, which covers all of the various representations of univariate extreme values when we're constructing statistical models. So the very first model that we saw last week was for block maxima. It considered the modelling of the maximum of a group of random variables is following a GEV distribution, and this follows from an asymptotic result that we're assuming applies at finite levels. So we're assuming that even though we only have the maximum of a finite number of random variables, that we're taking the number of variables large enough so that this asymptotic result is approximately correct. One problem with this approach to modelling is that it doesn't make very efficient use of the available data. So in this plot, I've simulated 10 years worth of daily observations, and the vertical lines are showing the separation between years, and the points in red are the annual maxima, which are the only points that we're including in our analysis. That means every year we use one of 365 available observations. There's so many large observations here that could be telling us about the tail of the distribution that we just aren't using. And it's not even a particularly informative set that we have here. So if we look at the fourth year, our maximum in the year 4 that we're including in the analysis is actually less than the second largest in year 5, which doesn't get included. What we want is to be able to include all of these large events when we're estimating our parameters. So one way around this is, instead of using the largest event in each year, to use the R largest events in each year. So for example, in this case, we're now looking at including the 3 largest events from each year and modelling the joint distribution of those 3 observations. This is good, and if we pick R to be large enough, then we might avoid that problem that we were having before. But if we're going to pick R to be fairly large, then what we might as well do is try and model all of the values that are sufficiently extreme at once. And this is what the peaks over threshold approach does. It says, okay, pick a threshold level U, and we're going to model exceedances of that level. We saw in the notes that the conditional exceedances of a high threshold U can be modelled as a generalised Pareto distribution with shape parameter psi, which is equal to the shape parameter of the GEV distribution, but a scale parameter sigma U that is different from the scale parameter of the GEV. This scale parameter sigma U is going to be dependent on the threshold that we pick as well. So what we can do is model these exceedances of a high threshold as IID observations from a generalized Pareto distribution. And this lets us use a lot more data than our block maxima, or potentially our largest approach as well. But how do we go about picking that threshold value U? How do we know when we've picked a threshold that is high enough for our asymptotic model to be valid? This is the same problem that we encountered previously when we were looking at block maxima, when we were trying to pick a block length that was sufficiently long that the asymptotic model held, but sufficiently short that we got lots of block maxima. Here we want to pick U high enough that our asymptotic GPD holds, but we also want it to be as low as possible so that we include as much data as possible and get good, precise parameter estimates. So to help us in picking what this threshold U should be, we can appeal to 2 properties of the generalized Pareto distribution. So if a threshold U is a valid threshold for the generalized Pareto distribution, then for any higher threshold V, the estimated shape parameter above U and above V should be consistent with one another. And the same can be said about the modified scale parameter. So remember that the scale parameter for the GPD is dependent on the threshold that we pick. But by making this transformation to sigma star equal to sigma v minus psi times v minus u, we get a scale parameter that is invariant to threshold choice. So what this means is we can look for a range of thresholds and say, okay, for which thresholds are my estimates for the shape parameter and the modified scale parameter consistent? And that'll help inform our decision. A second property of the GPD that can be used in a similar way is that the expected exceedance size, so the expected value of xi minus v, given xi is greater than v, should increase linearly as v increases above u. So to reiterate, that means that the size of our expected exceedance should get smaller as our threshold gets higher, and it should do so in a linear manner. What this gives us is two graphical methods for picking an appropriate threshold. The first is the threshold stability plot. So here we've considered a range of thresholds and estimated the modified scale and the shape parameter above each of those thresholds. Here the circles represent the point estimates and the vertical lines represent the 95% confidence intervals. For higher thresholds, these confidence intervals are wider because we're using far less data to estimate the parameter values, so our intervals, our estimates are less precise and our intervals are wider. For low thresholds, we've got much more data. Those intervals become much narrower. And what we want to be able to do is draw a straight horizontal line through back as far as we can, going through all of these confidence intervals. And we want to be able to do that for both the scale and the shape parameter. And what you can see from this plot probably is that that's not necessarily a straightforward thing to do. There's some subjectivity in how you interpret these plots. So appealing to our second method, we can again look at the expected exceedance size when using a particular threshold and look at that for a range of threshold values. So here the solid line is showing the expected exceedance size as a point estimate, and the dashed lines show a 95% confidence interval. Again, you can see that these intervals are a bit wider at higher levels, and that's because we have fewer exceedances to base this mean estimate on. What we want to be looking for here is a linear trend. So we want to see how far back from the right-hand side of the plot, the high thresholds, we can go while maintaining consistency with a straight line. And again, here you see that there's some subjectivity in this. So it may be around 0. You may even be able to argue that you can go down to sort of negative 0.5 here. So these give you a good way of getting good ideas about starting values for what modeling threshold you should be using. And what you should really do is go back and consider a range of threshold values that you complete your analysis above and show that your results aren't overly sensitive to that choice. So moving on from the peaks over threshold representation to the final representation, which is the point process representation. This actually encapsulates all of the previous representations that we've seen, and we'll look into how that links together shortly. But essentially what we've done here is transformed that previous peaks over threshold plot by squashing the x-axis to be between 0 and 1 and rescaling our y values so that we're now looking at normalized values using these constants an and bn that we were using back in the study of the GEV distribution. What this does is it means that small xi values are going to be squashed all together to the same value, and larger values are going to be retained as distinct points. What we saw in the notes was that for sets BV of the form T1 to T2 by V to infinity, so this upper rectangle here, or any subset of that in the time dimension, that the points occurring on that region can be well approximated by a Poisson point process as the number of points and the threshold increase. So what we can do again is assume that that asymptotic model holds a finite level and use this point process likelihood and intensity to estimate our model parameters. So we saw in the notes that the integrated intensity on BV is given by the width of the interval multiplied by the GPD survivor function for the lower value, so the survivor function at V. The associated intensity function, so looking at a particular point Tx, is simply given by the GPD density function, and that doesn't depend on T at all. Combining these into the Poisson process likelihood, we see that the likelihood of sigma u and psi is proportional to the exponent of the negative integrated intensity multiplied by the intensity at each of the observed event locations. And substituting each of these terms in, we can numerically optimize this likelihood function to obtain parameter estimates for sigma u and psi. So I mentioned before that this point process representation links all of the previous ones together. How exactly does that work? So for block maxima, what we're doing is considering a separate point process model for each block of observations, so perhaps each year of observations, and setting the threshold V to be equal to the largest observation in that period. That way, one observation is included in the likelihood for each independent Poisson process, and they combine to give you your likelihood function for block maxima. The R largest functions in a very similar way, but instead of just considering the threshold equal to the largest value, we set it equal to the rth largest order statistic. So, for example, the third largest value observed in that year. That way, R events are included in each Poisson process, and looking over all of them, we get R times the number of blocks is the number of observations included in our analysis. Finally, the peaks over threshold representation just looks at the events as a single point process and sets that threshold value equal to some high quantile of the distribution, where we're picking that value so that the GPD is an appropriate model. So that's everything I've got to cover in this video, and I look forward to seeing you in the examples class on Friday. Thank you.